In this video, we are going to have the proof of this lemma 6.5.2, which states that if T belonging to A of E is nilpotent, then this expression where the alpha I are scalars is invertible provided this alpha naught is non-zero. So the entire expression is in terms of the transformation. So these are all transformations. So here alpha naught I stands for the identity transformation. So if this is non-zero, then the entire transformation, okay, that is invertible. So in ring theory, somewhat similar to this, we had unit plus nilpotent. The sum of unit element and nilpotent is unit, not nilpotent. It is unit. Unit plus nilpotent is unit. So this is a famous result in ring theory. So this is also somewhat similar to that we have in vector spaces. You have these to be nilpotent, and this one I is always invertible, and when you have this alpha naught to be non-zero, only this one will exist. So you have this to be invertible. Unit means invertible. So unit plus nilpotent is invertible. Invertible means it is unit. So this result is somewhat similar to your ring theory result, and proof is also it also mimics the proof of the statement. So we will see how it is proved. You are given T to be nilpotent, and you are asked to show that this is invertible whenever you have your alpha naught to be non-zero. Now, since T is nilpotent, for some index R, you have T power R to be 0, and for lesser index, it is non-zero. And we shall take these expression, this one, to be say some S. So this is what we have. Now, we claim that even this is nilpotent. S power R is 0. So you consider S power R is what you have, and in all this T is common. So when we take it out, T power R, this is what we have. Alpha 1 I, T power R, T is taken out. So it is not T, it is I. Then alpha 2 T and so on. M here, M minus 1 raised to the power R. Because T power R is 0 from here, you have 0 transformation into some other transformation naturally gives you 0 transformation. Right. Now we shall consider. So this step is to be remembered. That is, you are considering the whole lot as S. That means you have the entire one to be just alpha naught I plus S. So with this, we are going to consider the product, namely I by alpha naught, and then S by alpha naught square, S cube, and so on. We need to have this to be a square. So you have up to this we have to consider. This needs to be memorized. And when you multiply this, okay, so this is what you get. Alpha naught I with this, alpha naught non-zero, cancelling that, you get I. And then alpha naught I with this. So that gives you minus S by alpha naught. And this one with this one gives you S by alpha naught. So this is with the plus sign and this is with the minus sign. So these two will get cancelled. So like this, when you multiply this, the last one will be S power R by alpha naught power R, and this suffix, this minus 1 power R minus 1 will be remaining as such. But how about the previous one? Alpha naught I with this will give you this. So one alpha naught will get cancelled. So you are getting alpha naught R minus 1, S power R minus 1. And we would have had in the previous one minus 1 power R minus 2, S power R minus 2 by alpha naught power R minus 1. So this one with this, that will give another term. That is what we have written here. So this one, whether R is even or odd, you will have, if it is R even, means this one will be, say some 4 you have, this one will be with the plus sign, and here 4 minus 1, so this same expression only, but one will be with plus sign, the other one will be with the minus sign when R is even. And if it is odd, means you will have this with the negative sign and this with the positive sign. So in any case, these all these terms will get cancelled, and this S bar R, because S bar R is 0 from here, this one will not be there. So you will be left only with this I, and so you're having something like this. See, when you have T composition S to be, say, I, then you say that this T is invertible, or you can even say that this S is invertible. So something similar to that only we have alpha naught I plus S. This is one transformation. With that, we are considering some other transformation. The product, the composition gives us the identity, which means this is invertible. And of course, in the same way, this is invertible, but what we need is only this. So that is this expression alpha naught I plus S is invertible. What is that we have assumed? Alpha naught non-zero. Just because alpha naught is non-zero only, we are able to have them in the denominator. So that condition is required. So we have um, unit plus nilpotent to be unit. So this result is somewhat similar to that of the same result in ring theory. Thank you.